Okay, so here's a problem. We have a beam with an internal hinge, rollers at A and C, and a pin at D, and we want to find the maximum moment at E, right here in the middle, a maximum positive moment. So the first thing we need to do is draw our influence line. So I'm going to come here at E, and using Müller-Breslau, I'm going to assume it behaves like a what? So I'm going to go ahead and I'm going to redraw the beam, and at E I'm going to imagine a hinge. I still have a pin here, a roller here, and a roller here. Now what do we do with Müller-Breslau is we release that and then we apply positive moment. So how will that point E move? Will it move up or down? Looks like it's going to move up. And as it moves up, then it would hinge like this, seesaw over this edge, and then link back like that. So that looks like the shape of my diagram. So far, so good? So if I were to draw that now, formally, I'd say the moment at E would look like this. So I'll just redraw that. Now what do I need now is I need some values. Now before we decide what we're going to do, I may not have drawn this exactly to scale, but all of these links are 4 meters. So what does that say? Similar triangles tells us that whatever this height is, it'll be the same value here but negative. So you can decide whether to work the problem by putting your unit load here or here. I think this will be the better position of the two. So what that means is that our unit load, our moving load, will be at E, and I'm trying to find the moment at E. Okay? So that means if I draw that particular scenario, I still have my roller at A, roller at C, and my pin at D. And now I'm going to let my unit load be right here, right at E. So this is the position I'm trying to find. I'm trying to find the moment here. So you can see if I were to cut the structure at E and look at the left or the right-hand side, it looks like the right-hand side is going to be the easiest one to do, which means all I need is the reaction at D. So I need to find my reactions at D for this scenario. So what I'm going to do is I'll quickly break this up into 2 free bodies. So if I look at this left piece from the hinge over, I'll have a reaction at A. And this is B. I'll go ahead and assume a reaction at B, By, Bx. And then of course it's equal and opposite on the connecting body. This again is Bx and By. And then I'll draw the free body diagram for BCED. And there I'll have a reaction at C, the roller. And then all the way over here, the reaction I'm really looking for, the reaction at D. And don't forget my unit load is here. So looking at these 2 free bodies, you can see that down here on the left-hand side, well, there's no load, so all these forces are 0. So if Bx and By are 0 on this free body, they're 0 on this free body. So then all I have to do is what? To find By, I'll just sum my moments at C on this free body here. So if I sum my moments at C, I should be able to find dy in terms of 1. Don't forget, I did forget. to go ahead and put my units. These were all 4 meters. So if I sum moments about C, I'm going to have a negative moment created by the unit load 1 times a 4 meter moment arm, and then a positive moment created by dy and an 8 meter moment arm. So it looks like dy is 1/2. Okay? So now I can come here and actually cut the structure at E. So there's my unit load. I have the actual internal moment that I'm looking for, the moment at E. And I have my reaction, dy, which is 1/2 up. And this length is 4 meters. So all I have to do is sum moments at the cut and make sure it's in equilibrium. And with right-hand rule, this ME is negative, and this 1/2 reaction is positive. 1/2 times 4 meters. So it looks like the moment at E is equal to 2 meters. So that means I can come back up to my influence line and say this is 2. And similar triangles tells me this is -2. And let's not forget the units are meters. So I'll just break that off a little bit. So now up here I'm going to actually solve the problem. So I have my influence line now. Now the problem, I didn't write this down, but if you look back, it says that we have a single live load of 45 kilonewtons. So we'll do the live load first. So it's 45 kilonewtons. And we're trying to find the maximum positive moment. So where do I put that live load on the diagram to create the maximum positive? Right here at E. So that'll be 2 meters. So I'll multiply that times 2 meters. And that component gives me 90 kilonewton meters for the moment. Or that component of the moment. Now we have a live uniform load. And that's given as 1.4 kilonewtons per meter. Now where do I put this uniform load, live uniform load, to create the maximum positive moment? Well, I don't put it at all on the first 8 because that creates negative. So I just put it on the second part of the thing, or the beam, this 8 meters. So the area under the positive part of the curve would be this triangle, so it's 1/2 the base, which is 8 meters, times the height, which is 2 meters. And that looks like you get 11.2. That sound? What's 8 times 1.4?
8 times 11.2.
11.2 kilonewton meters. So there's the component or contribution to the moment of that. And then finally, the dead uniform load. Now, on the dead uniform load, do you get a chance to locate it where it does the most effect? No. You have to run it over the whole beam. In this case, the dead uniform load is 0.5 kilonewton per meter. And you can see in this case that the negative area and the positive area are equal.
Is that the same thing, even if it's the dead weight is the weight of it, or it could be just a regular dead weight?
Yeah.
There's only one dead weight. There's no choice in dead weight. Dead is the total length, the whole length. So, I mean, mathematically, if you did it, you would see that you'd have 2 triangles, right? One that has a height of -2 and a base of 8, and one that has a height of 2 and a base of 8. And you can see that that makes no effect. So the total moment, positive moment at E, would be the sum of these two, which looks like it's 101.2. So there's the maximum moment. And just to show you again, to emphasize what this would look like, I'll redraw the beam. Roller at A, roller at C, pin at D. So in one case we have the dead load, which is across the entire structure. So that's the dead load, and I think in this case that was 1/2 kilonewton per meter. And then we have the live load, which is just over the last 8 feet of the structure, and it was 1.4 kilonewtons per meter. And then we located the concentrated load here at E, which is right in the middle. So this is the loading configuration that generated this value. So any questions about that? No question? Okay, so I'll stop that.